Hello everyone. Today let's dive into chemical reactions, the process that transforms substances into something new. You see them everywhere, milk turning into yogurt or an iron gate rusting. In a chemical reaction, reactants change into products with different properties. Think of baking a cake. Flour, sugar and eggs become something entirely new. To describe these changes, scientists use chemical equations, a shorthand using symbols and formulas. For example, hydrogen and oxygen react to form water, H2 plus O2, H2O. The left side lists reactants, the right products. The arrow shows the direction of change. We also note physical states, S for solid, L for liquid, G for gas, AQ for dissolved in water. For instance, CS plus O2G, CO2G, tells us carbon solid reacts with oxygen gas to form carbon dioxide gas. Including states gives a clearer picture of the reaction. Chemical equations are the universal language of chemistry. They let scientists everywhere understand and replicate experiments. So, next time you see rust or baking, remember, it's all chemistry, written in a universal code. Let's see why balancing these equations matters. Chemical equations must follow the law of conservation of mass. Mass is neither created nor destroyed. Imagine building with Lego bricks. You can rearrange them, but you never gain or lose bricks. In chemistry, the number of atoms for each element must be equal on both sides of the equation. Take H2 plus O2, H2O. To fix this, we use coefficients, 2H2 plus O2, 2H2O. Now, both sides are balanced. Balancing equations ensures our recipe is accurate. Next, let's explore the different types of reactions you'll encounter. Chemical reactions come in several main types. First, combination reactions. Two or more substances combine to form one product. Example, CaOs plus H2OL, KOH2AQ. The beaker gets hot, energy is released. Next, decomposition reactions. One compound breaks into simpler substances. Example, 2-pheso4S, Phe2O3s plus SO2G plus SO3G. Heating ferrous sulfate changes its color and releases gases. Combination is like two people becoming a couple. Decomposition is a breakup. These patterns help us predict products and understand real-world changes, like rusting or baking. Recognizing reaction types is key to mastering chemistry. Now let's look at how elements can swap places in reactions. This leads us to displacement and double displacement reactions. These swaps are the basis for many important chemical processes. Let's see how they work. On to the next type. Displacement reactions occur when a more reactive element replaces a less reactive one in a compound. Example, place an iron nail in copper sulfate solution. Iron displaces copper, forming iron sulfate and copper metal. Phes plus QSO4AQ, PheSO4AQ plus Qs. The nail gets a copper coating and the solution changes color. Double displacement reactions involve two compounds swapping ions, AB plus CD, AD plus CB. Often one product is insoluble, a precipitate. Mix sodium sulfate and barium chloride solutions, Na2SO4AQ plus BaCl2AQ, BaSO4s plus 2NaCl, AQ. A white solid barium sulfate forms and settles. Precipitation reactions are key in labs and industry for separating substances. These reactions show how ions interact in solution. Watching a precipitate form is a clear sign of a chemical change. Understanding these swaps helps us control and use chemical reactions. Next, let's see how energy changes in reactions. Energy flow is crucial in chemistry. Chemical reactions involve energy changes. Some release energy, others absorb it. Exothermic reactions release heat, surroundings get warmer. Example, burning wood or mixing CaO and H2O. The reaction KOs plus H2OL, KOH2AQ, plus heat shows energy released. Combustion reactions are exothermic and power our homes and vehicles. Endothermic reactions absorb heat, surroundings get colder. Example, dissolving ammonium nitrate in water makes the beaker cold, used in instant cold packs. Photosynthesis is endothermic. Plants absorb sunlight to make food. In equations, exothermic reactions show heat as a product, endothermic as a reactant. Recognizing energy changes helps us harness reactions for practical uses. Whether heating or cooling, energy flow is at the heart of chemistry. Next, let's explore reactions involving electron transfer. These are called redox reactions. They're everywhere in daily life. Oxidation reduction redox reactions involve the transfer of oxygen, hydrogen, or electrons, oxidation gain of oxygen or loss of hydrogen, reduction loss of oxygen or gain of hydrogen. They always occur together. One substance is oxidized, another reduced. Example 2. Q plus O2, 2QO. Copper gains oxygen, oxidized, reverse it, QO plus H2, Q plus H2O. Copper oxide loses oxygen, reduced. Hydrogen gains oxygen, oxidized. Think oil rig, oxidation is loss, reduction is gain, of electrons. In Fe plus QSO4, FeSO4 plus Q, iron loses electrons, oxidized. Copper ions gain electrons, reduced. Redox reactions drive rusting, respiration, batteries, and more. Sliced apples turning brown? That's oxidation. Photosynthesis and respiration are both redox processes. Understanding redox helps explain corrosion, energy production, and life itself. It's a core concept connecting chemistry and biology. And that's the world of chemical reactions. Transformation, energy, and the flow of electrons.